So today the plan is as follows. So we will now go more into the mathematical analysis of the BKT, and I will do the following things. So the first part is I will prove one proposition which justifies the decoupling of villain, and I will recall the three main definitions in a second. The decoupling of the villain model into a GFF times an independent Coulomb gas. And more exactly, we will have the discrete derivative of a GFF times the d star of something which has to do with the Coulomb gas. I will recall this definition in a minute. I will recall this definition also in a minute. This has to do with the vortices or the topological defects of these S1 valued spin systems. And I will make a little crash course, small crash course on those notions, the D star, and what do I mean by a discrete differential calculus. And with all those tools, we'll have a decoupling of the S1 valued model into a Gaussian free field, something which is Gaussian, which is sort of easy to understand, and something which is more delicate, which is the character responsible for the Berezinskii-Kosterlitz-Thouless transition. In the second part, I will tell you about a proof of BKT. So I will do not a complete proof, but I will give you the main argument. And the initial step here will be that the Fourier transform of S1 is Z. And in a nutshell, what makes the BKT phase transition very strange at first sight is that there is never any long-range order. At high temperature, the spin system is exponentially decorrelated. And at low temperature, it still doesn't have any ordering, but there is this quasi-long-range order, which is a bit subtle and beautiful at the same time. But once we Fourier transform the spin system, here it's a more classical phase transition in a sense, which has localization ordering in one side and delocalization non-ordering in the other side. So that's why probably the mass proofs, they always go through this, because this one is more classical in a certain sense. And maybe there will be a third part, but as usual my timing will be off, so probably this will be good enough. So maybe some recap, some small recap. So I spend some time defining S1 valued spin system on Z2. I spend some time discussing the XY model. I will not do it again. I will just maybe put one formula. It can be viewed as a collection of random angles on the sides of a box lambda. And this was product over the nearest neighbor vertices of exponential beta cosine theta I minus theta j. And just to start using notation, I will define more precisely in a few minutes. I could rewrite this d theta along the edge ij. So this is the XY model, and on a finite box of Z2, this samples angle in the unit circle S1, which tends to align in the same direction when the inverse temperature beta is large. And today, the main character will be a slightly different model, which is also S1 valued, and this is the villain model. And it's also a probability measure on a collection of angles. The only thing which changes is the interaction along the edges of the graph. So here, the probability measure against d theta, the uniform measure on all those S1 circles everywhere, is now proportional to the product along edges of, I will write it in two different ways, either as follows: sum over the integers m in z, exponential minus beta over 2 theta I minus theta j plus 2 pi m square. So this is a 2 pi periodic function of the angles, which is more happy, which is bigger when theta I is close to theta j. So we say this is still a ferromagnetic interaction. And when beta is large, it looks a lot like the xy interaction that I have here. A second viewpoint here, but it's the same thing, is that this expression here is nothing but the heat kernel of the Brownian motion on the unit circle S1, computed at time t equals 1 over beta. So he will always use 1 over beta, but sometimes in this setting, the temperature T would be more natural. So it's the heat kernel between angle theta I at one side of the edge and theta j at the other side, with this time T equals 1 over beta in between. So this gives also a ferromagnetic interaction, which is such that if beta is large, the angles want to be more or less in the same direction. So that's a recap for this model. The GFF, I will not recall what this is, or maybe in a tiny box here. The probability measure lambda beta GFF. This is proportional to exponential minus beta over 2 the L2 norm of the gradient, and maybe to make things well defined, phi at some point x0 is equal to 0. So the GFF is a Gaussian process. It's simple. One can understand the fluctuations. The villain process is more interesting. And the last character before I start is the Coulomb gas. So here, in our setting, it will be a probability measure. So I will stick to dimension 2. It will be a probability measure on the integers to the power the faces of the graph. So if I have a lambda n by n box in 2 dimensions, my probability measure will sample a field of integers on the faces of the graph. So each face is equipped with one integer, and I need to define a probability measure which will output this collection of integers here. And this probability measure will be, I will call it Coulomb. If it's in the faces of lambda at inverse temperature beta, this will be proportional to exponential minus beta over 2, and then Q against minus Laplacian, and this Laplacian lives on the faces of lambda, inverse Q, and that's it. So what I mean by that is that it's proportional to exponential minus beta over 2, sum over I and j, qi, qj. The green function in some sense is the dual of the graph lambda at position I and j. And there is one last thing I need to comment on. I will not spend too much time on this, but in statistical physics, when we define a model, we need to prescribe boundary conditions. And there are three sets of boundary conditions which are natural. There is the free one, the Dirichlet one, and sometimes the periodic one. And I could also add maybe Dobrushin and less isotropic boundary condition. I will not look at those. Here I will stick to free boundary condition on the villain side. And if I do this, the Laplacian I need to consider on the dual side is the Dirichlet one. So free on the S1 valued system is mapped to Dirichlet on the Coulomb gas, and Dirichlet would be mapped to free. So the only thing I will say is that when we invert such a Laplacian, of course we need to be a bit careful with which Laplacian we are working with. And the boundary conditions imposed are induced by the model we are looking at, but they are reversed because we are in the dual phases. So now I have this model. I recall the definition. I quickly recall this one, which is a R-valued field, which is Gaussian. It's a Gaussian random vector. And this is a field of integers on the faces of the graph. And what I said last time is that the way they live together can be viewed like that. If we sample the villain model, but we add an additional randomness, given this villain model, we can complete the information along the edges by sampling, given those angles, a Brownian motion on the unit circle from this angle to this angle. So I don't know how to draw it, but along one edge, if this is theta I and this is theta j, what I do along this edge is that I do a Brownian motion of time 1 over beta, conditioned to be back at this point at time t equals 1 over beta. So maybe this we don't see anything, so let me do it better. Maybe this is theta I. Maybe this is theta j. And I want the Brownian motion on the unit circle, so I will do a Brownian motion of time t equals 1 over beta. And I condition it to reach either theta j, but maybe also theta j plus 2 pi, maybe theta j plus 4 pi, maybe theta j minus 2 pi, minus 4 pi, and so on. And maybe my condition Brownian motion is going to do this, which is not my picture because it should do at least one term. So if I sample a villain, that's my first layer of randomness. Second layer of randomness, I add IID Brownian bridges between those angles. So S1 Brownian bridges. Third step, in each phase, I can compute the local monodromy around the phase. If I do this, I will collect a field of integers which live on the faces of the graph. And what I claim is that this field of monodromies is exactly the Coulomb gas that I defined over here. Monodromies is a Coulomb gas. So I will state the proposition that I stated last time. So I will do it in the reversed order. So there is an old proposition, which is in fact the one I will prove. This is the main input of several things we extracted out of it with Avelio Sepulveda. And this one goes back to Rosset, Kadanoff, Kirkpatrick, Nelson in 1977. And it's the first time we could see a decoupling between these three models. And this says that the partition function on a finite box of Z2 lambda at inverse temperature beta for the villain model, this is equal to the partition function of the GFF on lambda beta times the partition function of the Coulomb gas on lambda star 2 pi squared beta. Paul, is there a question? I can hear you very well from here.
Is this a product?
Yes, you're right. I don't need a fancy sign, it's just a product. So I have a partition function of the villain, and I claim they noticed that the partition functions decouple between those two systems. And that's the very main input to this story. And what we did with Avelio is a small extension of this. We looked at what does it mean probabilistically on the theta, phi, and q models. And we extracted the following proposition from which we could get many corollaries that I will give later on in this talk. So I will not prove the second proposition, but what we have is that if theta is a villain model, the natural one form we can produce out of the theta is equal in law to the d of GFF phi plus, I don't know how to write it, but this means independent, plus something which is built out of the Coulomb. So at this stage, I would just want to put d star Coulomb, because even d and d star are not properly defined yet. But later on, this formula will make sense. It will be plus an independent d star. There will be a 2 pi d star Laplacian inverse of q. And this equality has to be read modulo 2 pi. And already last time, I gave a first corollary of this expression, that the 2-point correlation function cosine theta I minus theta j, or theta x minus theta y, this expression can be decomposed into the contribution of the GFF times, by independence, the contribution of the Coulomb. So maybe this, I will redo it. It was the last 2 minutes of the lecture last time. Cosine theta x, so application 1. I will give several other applications after the proof of Rosset, Kadanoff, Kirkpatrick, Nelson. Application 1, cosine theta x minus theta y for the villain model at inverse temperature beta. By symmetry, this is the same as e to the I theta x minus theta y. Now I can use this expression that I have here. It will be e to the I phi x minus phi y for a GFF in lambda at inverse temperature beta times real times, there is no circle here, expectation of EI, and here I don't want to write it, some d star which depends on the Coulomb, something complicated. At this moment I don't need to write what this is, the only point is that this is less or equal to 1. And so all this is less or equal to E minus 1/2 variance under a GFF measure at inverse temperature beta of phi x minus phi y. And if you were not here last time, it's not very important, but last time I explained why one can compute those. This is a Gaussian process. It's just something that you can express in terms of random walk because it's a Gaussian process whose covariance matrix has to do with the green function. And so it's not very hard to see that this is less than 1 divided by x minus y to the power something like 2 pi divided by beta. And in the course number 1, we had a proof of Mermin-Wagner which gave something weaker, which was less than a constant of beta 1 over square root log distance between x minus y. So at least for the villain model, this viewpoint readily gives polynomial decay in an easy way. What it doesn't give is that there is a BKT transition. It only gives an upper bound which is polynomially decaying whatever beta is. And the truth is that in fact it's exponential at small beta and it's lower bounded by a polynomial at large beta. That's the transition. So now I will do the crash course, unless there are questions.
Does such an idea applies beyond Z2? Or?
Yes, so it works. I really like it. So beyond Z2, so if I was in 3D and I were to do the, so it applies in a very general way. So if I was interested in the villain model, I could put a villain model on the vertices of Z3. And then what would happen is that the villain field will decouple into a GFF on the vertices of this three-dimensional box. But the Coulomb gas would not be the classical Coulomb gas. It would be a Coulomb gas which lives on the plaquette of Z3. Still, you can look at it, define it, use it to prove you're not going to prove something like that because the green function in Z3 is not logarithmic, so you're not going to have a very interesting upper bound. But you can definitively do this decoupling and start to play with it. I will even give an application. A second thing you can do, if Thierry is in the room, yes, Thierry is there, so you can do lattice gauge theory in Z3, which is a kind of S1 valued model carried now by the edges. And if you do this, you still have a decoupling of a model on the edges of Z3, which will decouple into a GFF on the edges of Z3. But now the Coulomb gas is the nice Coulomb gas on Z3. And using this, one can do the bi-screening. And there will be some applications to this later on in this talk. So yes, it can go to Z3. But today, except when I will say there are applications, my crash course will stick to Z2 because there are less, I don't want to go into n cells, and there will be 0 form on the vertices, 1 form on the edges, and 2 forms on the faces, and that's it. This is good enough for the crash course. Are there other questions before I?
It's also not specific to lattices. You can take
yes, so this I'm less comfortable with, but indeed this feels a little bit like a Hodge decomposition of a one form. So maybe one could imagine a statistical physics model on S1 valued spins that live on R2 and may have some singularities. And then we could play with this. What is not completely clear to me is what would be the nice smooth enough interaction on the whole R2 which would still nicely decouple like that. So the Z2 has the role of a ultraviolet cutoff so that everything is well defined. It's true that those decompositions, they go beyond lattices, but then I would need a crash course on the real differential calculus without lattice, which I will not do.
Or maybe just graph, like more general.
More general graph, yes, completely, yes. For example, everything I will say would work perfectly for planar graphs. For non-planar graphs, then it goes a little bit into the discussion I just did here. But planar graphs, I don't need the periodicity of Z2 at all.
For non-lattices in dimension 3 and higher, what would be the analogous plaquette?
For non-lattice, you mean on R3? Graphs.
Nothing else assumed.
So if your graph is embedded into R3, you can still play with plaquettes, 3 cells and all this. Then the whole edifice, I don't know, the whole structure will work very well. If you have an abstract graph, so for example, I ask myself what's going on with the long-range Ising or XY, which is very mean-filled. There, you can formally do it, but it's a bit nasty. You have too many structures to... So I don't know a very good generic way of doing this. There are many books on discrete differential calculus who try to affect the right... You will see there will be a tower, the 0 form, the 1 form, the 2 forms, with some operators going from one to the other. If you can do such a structure which is strong enough, then you can work. But if it's too general without, I don't know. If you have a hyperbolic planar graph, you're in very good shape, for example. Okay, so I'm not at all an expert in a discrete differential calculus, so I will make the crash course very small. And I will only list the few properties I need. But just to get a feeling of what is going on, I will put a couple of very small exercises that I will solve on the spot except one. So crash course. So maybe I have lambda, a sub-box on Z2, and I will just need to be able to do differential calculus on this finite piece of lattice. Maybe let me make it a little bit bigger. So maybe this is a large enough finite box of Z2. And on this box, I want to tell you about 3 different objects. Maybe I will have the 0 forms, which we can think of those as normal functions. And I will denote those by omega 0, but I think it's the only moment I will use this notation, so don't pay too much attention. And maybe I can give an example in this side of the box of a 0 form of a function. Maybe I have a 5 here, 2 here, 0, 0, 1, something like that. So a 0 form is just something which gives one real number to each vertex of my graph. So nothing fancy, very. And then we'll need something else, which is the 1 forms. And those, as I explained last time when I told you about the physics intuition of the BKT phase, what is very relevant when we look at a vast collection of angles on the Z2 graph is the relative angle along one edge, which, if beta is large, is usually something close to 0 modulo 2 pi. So 1 forms will be very important. They have a name which depends on the context. The name is not very important. And what is a 1 form? Maybe I can draw one in this part of the domain. This will now be a function on the edges of the graph, not on the vertices. And it will have one further structure. It will have a direction. So maybe I have a 2 here. So it's a function, maybe f is a 1 form. if f belongs to the space R to the power the directed edges of the graph. So each directed edges carries a real number, but I want that f of E is equal to minus f of minus E. What does that mean? It means if I have a flow of 2 in this direction, if I were to go along that edge in the reverse direction, I would need to see minus 2. That's all what I need. So, in principle, you could have the same condition on the zero form if you have an orientation of the vertices, but I will not need any of these here. Okay, so maybe a one form is something where you have some flow. You could only keep track of the positive if you wish with a... And it's a field of not necessarily integers at this moment. This could be 7.6 on the edges of the graph. In fact, it will not be an integer very quickly. And then I have two forms, and that's about it. Two forms, omega 2. That will be a field of real numbers attached to the faces of my graph. So now maybe I can draw it here. Two forms is something which will be on these faces, and maybe this is a plus 4.2, minus 0.6, plus 11, 0, 0, 0, 0, something like that.
Perhaps it's r to the power.
Oh yes, thank you, thank you. Yes, this is r, but in fact this one we will only have integers. But yes, you're completely right. In this setup this is r, and we will use it for z to the f to the lambda. So in fact also here there is a, as for the vertices, I'm using this orientation of faces. I will not need to use the reverse orientation, but if you do discrete differential calculus, you may want to orient the plaquettes as well. So three objects, zero forms, one forms, two forms. And one of the whole points of differential calculus or homology or whatever you call it is that there are natural operators that go from one to the other. And I will call those just D. So this will be the discrete differential operator. In some other context, one would remember from which space we go. So if we go from the zero forms to the one form, some references would call this one D0 to 1, and this one D1 to 2. But I will not. It will always, if I take the differential of a form, it will be implicit. If I am differentiating a zero form, I will know it's a D of a zero form, and I don't need to prescribe indices. So there is the differential operator, and there is the co-differential operator, and in fact this one, we will see that this will just be related to the adjoint of D. So I can already define it now before defining D. D will be defined as minus the adjoint of D star. So minus adjoint. So before I give you the definitions will be extremely simple, very concrete. Maybe I will start with an analogy because maybe you are more familiar with continuous differential calculus. So I will start with one analogy. So if f is a smooth vector field from Rn to Rn and vanishing at infinity. This assumption is just because I did this example in the train this morning and I don't want to mess it up with my integration by parts. G is a no, I want this to be a scalar. Sorry. Scalar field. G will be a smooth vector field. So from Rn to Rn. And a classical formula that we use in a continuous differential calculus, and we will not use something much fancier than that, is to try to understand the integral over Rn. G is also vanishing at infinity very nicely. No problems of integration. You may want to integrate the gradient of f scalar product with G, all of this x dx. And if I did not mess it up with my integration by parts, no problems at infinity, this is easy to be minus integral of f of x against the divergence G of x dx. So I claim that here f is a zero form, it's a function on Rn. This will play the role of the discrete differential form, and the duality here is the integration by part, and in discrete it will be just a discrete integration by part. And the d becomes, so the d star will be minus divergence in continuous, minus the adjoint. So what does it? Okay, so maybe I will give the definition now. So if the most difficult in this crash course is to give good names for the forms. So if G is a zero form on lambda, so this means G lives in R to the power lambda, I want to define something which looks like a gradient operator. And this will be very simple. I will define dg on the edges ij to be just g of j minus g of I. G was a bad choice because with I and j I get confused. But just the gradient of this function along the edge with this choice of your orientation, end of the edge minus beginning of edge. So this is more or less what we do with a gradient, except there is nothing infinitesimal here. So that's my D. What will be my so I just define this D. Now I will define maybe as I did in this analogy, I will define D star from the one forms back to the zero form. So to define this, I would just need to do a discrete integration by parts as we do in this setting. And it turns out that D star of the one form f, I have used f here. So I take a one form which is defined on the edges. I take the D star, so I will now define what this is. And to compute this, after the action of D star, I end up with a zero form. So this should output one real number per vertex now. So my formula should at least do this. If I take any point x a point in lambda, I should have some real number which collects whatever it needs to collect on the edges of lambda. And I will define this to be sum over y neighboring x, f of y minus f of x. So this is what we call a discrete divergence. So this is exactly what I feared before, that I have a minus I didn't want. So here, no, maybe that's good. So
Perhaps it's f on the directed edge from x to y, because f is.
no, thank you. This is important. So this is sum over y neighboring x of x f x y. Yes, thank you. Because f is a 1 form and I was pretending it was a 0 form. Okay, so if I do this, yes, very good. So if I do this, we see in the continuum that the adjoint of the gradient is minus the divergence, but my d star is minus the adjoint. So d star in the continuum would be minus divergence, which is plus divergence, which is consistent with what I'm doing here. Okay, and similarly so we just defined how to travel from 0 form to 1 form and back. Now I want to quickly tell you how to do things from omega 1 to omega 2. I will give less justification, but it's the same type of idea. So now if I take a 1 form f and I differentiate it, I want to produce a 2 form. So f is really bad because my faces, I like to call those f. So maybe my face will be a big square A. And this will be f of E1 plus f of E2 plus f of E3 plus f of E4, where A is a plaquette in Z2 like that, and it's oriented like this. I'm using planarity here to have a consistent orientation. And when I take one form in my graph, the d of the one form of that plaquette A, I just sum along the edges around A the values of the one form on those edges. So for people doing lattice gauge theory, you can see that this is very Abelian what I'm doing. I don't even care in which order, this is completely Abelian. So that allows me to go from one to the other, and the minus adjoint of this, it's something which could take a 2-form W and produce a 1 form, so I need to be able to read what it does on one edge I and j. And I claim that this will be, let me call this E. I claim this will be defined as W Fe plus, my notations are bad, I will do a drawing, WFE minus. So what is this? I have an edge, directed edge I, ij, my edge is here, and I have 2 forms in my graph. So maybe I have a face, the face F plus here, the face F minus here. And given these 2 forms, I produce a 1 form by taking the gradient around the perpendicular direction. Okay, so that's the worst part of the crash course. I will try to make the example above. And this was not prepared, so this is a... let's see, so if we do this, and I take this 1 form and I want to produce this 0 form, and I want to produce a 1 form. Along this edge, I will take 5 minus 2. So this will be 3. Along this edge, I will take 5 minus 0. I will get 5. Here or here, I have 0. Here I have 2. And so on and so forth. So given a 0 form on my graph, I can produce for you a 1 form. What would be very pedagogical, but it's too messy here, would be that I could, given this 1 form, I could produce a 2 form out of it. So I could apply this D operator on the 1 forms and try to see which two forms do I have? So maybe let me try to be pedagogical. Let me zoom. If I differentiate again the zero form that I started with, so I have 5, 3. So if I have 3 like that, it means that I have -3 in the other direction. That's the constraint I did put on the one forms. Then I have -2 like that. And here or here I have 0. If I compute the d of my first zero form, which was maybe g, on the face A that I have here, I can see that I have 0. And in fact, this will be this is not by chance. If you turn around those points and sum the gradients of a zero form, you will quickly guess that it must be 0. But the fact d squared is 0 will be important and will be in my list of properties. If I go to this, I could produce a 2 form out of that. So maybe this missed some data. Let me put 0. So if I have a 1 form, I can try to produce a 2 form. Let me go to this face. I will take -6, -2, +1, so it's -7, +0. So this face will carry -7. And I will not do the pedagogical backward to play with the d star. These are very local and very simple operators that apply to k forms and go to k+1 or k-1 forms. I will now list important properties of those, but if there are any questions on the definitions, I'm happy to stop.
So going back to general graphs, even the Z3, in the planar case, faces are kind of a basis of cycles.
Mm-hmm.
But in 3 and high dimensions, it's not. There are some ambiguities. So it generates everything, but it's not a basis. So, for example, if you take the plackets around the cube, you have some linear dependence there. So isn't that?
Yes. So I think.
That's the defined in this case.
I think the ambiguity you're talking about faces in Z3 is of the similar kind as the one forms in Z2. That the orientation there is very important. So in Z3, if I have a face, I need to ask here really about an orientation. And once I have an orientation, I can if I had a one form, I can put a 2 form inside this placket. And if I view the other orientation, I would go the other way. And also, if I have a d star of a 3 form, so something which would take values in the cubes, when I take a placket with an orientation, I will take, if it's this orientation, I will take this value minus this one. And if it's the other direction, I will do the reverse. So the plackets of Z3, they don't have an intrinsic orientation in the same way as the edges of Z2, they don't. But then the 3 cells of Z3, maybe you can choose the same orientation for all of these if you want, as we did here. I don't know if this answers the...
But you get an exact sequence each time when you apply the operator.
Yes, exactly. So on Z3, I would have now omega 0, omega 1, omega 2, and omega 3. And there is an exact sequence, and you can use like the kernel, the images, the homology if the graph is more complicated, and everything. The homology is a bit the degrees of freedom that are remaining.
Is it so you would have your decomposition would have Coulomb gas on the plackets, right?
So it depends. If I do the villain model on Z3, the Coulomb gas will live on the placket.
Right, but so then these plackets this Coulomb gas doesn't need to satisfy some non-ambiguity thing that the sum over cube is equal to 0 or something?
That depends on the boundary condition. And no, so the analog here would be, can one define a GFF on the one forms? So the analog of what you're asking a bit on the 2 forms. And yes, we can. I will not go too much into it, but yes, we can. And in fact, the Laplacian is invertible on those, so everything is very nice. But it's just when you look at this statistical physics model, it comes with an orientation. The value along one edge is minus the value on minus edge, but it's well defined.
But it doesn't fill the whole space, right? Because it lives in the image of the D operator. But now because you have another one in the exact sequence, it means the image is not the entire.
Yes, so what Pete is saying is that the Coulomb gas you would have on the plaquette is much more local than the Coulomb gas we need to play with. Which in fact makes the analysis simpler, but the one we're playing with has very like these log correlations, and that's what make it more difficult.
Is that right to say I can consider D star as the D on the dual graph?
Yes, so this is Poincaré duality. Exactly, and in fact this will be. In this setting, this is very easy, but this will be quite important. At some point, we will move to z-valued models, like z-valued Gaussian free field on those faces. And the way we will think about those is really as zero forms where we take a gradient, exactly like you say. So we will use Poincaré duality, but in this setting, it's a much simpler duality than in, but exactly. So that's also why I don't need to spend too much time on from one form to two forms. It's kind of the same mechanism as from zero form to two forms, but with a pi over 2 twist a little bit. And any other question? Don't hesitate, because then I will use those.
So, sorry, this Poincaré duality, then does that imply something about your measure, the villain?
It will not say that. It will not say that this is the same as that.
But there's something else.
So there is a nice duality, but it comes with some subtleties. The boundary conditions are changed, for example, and in the definition that I think I erased, the Coulomb gas. The interaction is with the Laplacian inverse, not a Laplacian which would be this one. So also the operator gets reversed in some sense. So for the statistical mechanics, the duality is not easy, this one. But for the structure of the 1, 2, 1, 0, 1, 2 cells, this is very symmetric. But the probability measure, this is less symmetric, the way it goes through the...
Maybe there's another model for which there will be the...
Yes, so I think if you do the GFF on the one forms in 2D, the fluctuations produced for the GFF on the one forms, this was I think observed by Yuan Aru, is equally produced by things coming from the zero form and things coming from the two forms, both Gaussian type, both white noise going to here. So there is a very nice symmetry. But if we have, if we break the symmetry with S1, we get Z on the other side, and so that's less symmetric. So maybe I keep the part of the crash course here, so that the properties will be next to the definition. So I will not need many properties, but a few. So properties. So they're all very classical. The first one is that if you compose D with itself, so this applies to zero forms and outputs two forms, this is always zero. And this is a reminiscent of what analysis would say as a curl of a gradient is zero. So now that I was in contact with discrete differential calculus, each time, which doesn't happen very often, I am in contact with such analyses, I go back to the discrete and I don't say something wrong, usually. So the other one is this, but this is just a consequence of the first one. A consequence of both is that if I take the space of one forms which is produced by differentiating the zero forms, this will be orthogonal to the d star of the two forms. This is just a consequence of this. And in fact, this is quite important. This will play an important role in the proof in a few minutes. And you can already maybe guess that this orthogonality has to do with the independence that I stated earlier. So this has to do with the independence between the GFF and the Coulomb gas. And it's a very easy corollary of those definitions that I gave here. I mean, it's a corollary of this, basically.
This is the inner product coming from the Clay energy?
Yes, so if you want to see it as an inner product, it just says that the D, what was my name, of a zero form G, scalar product with D star of a two form W. So this is a two form, this is a zero form, but thanks to those operators, they live on the same. I didn't define the scalar product on one form, but this, the sum of squared along the edges. Since D star is minus adjoint of D, this is maybe minus D squared G against W. So that's good, that's a two form against a two form, but D squared is zero, so this is zero. So I don't know if this is what you meant, but yes, it's exactly this. So this is the proof of that. So that's a nice property. So a proposition which is called point carré lemma. So here I will go a little bit fast by saying that if F is a one form, but it would also work with a two form, and here there are no conditions. Here there is a condition that such that D of F as a two form is zero. So if you have a one form, which is such that along each placket, when you do this rotational around the placket, you always find zero, then you can always find a zero form. There exists a zero form G, such that D of this zero form G is equal to F. And this point carré lemma, here I'm using the geometry of my graph. So I will just give a counterexample. Yes, so let me imagine that I am on the torus. So maybe let me put not always true. So on the torus, let me take the following example of a one form. Oh, my one forms were in yellow. It started a bit pedagogical, but it's going away. So let me imagine that my one form is this field of edges that I set to be equal to 1, and all the other edges I put 0. And this is all along the torus in this part. If this is my one form F, D of F, I claim that this is equal to 0. Why? If I take a face here, if this is my face A, and I take D of F along that face, I will have 1 plus 0 plus minus 1 plus 0, which will be 0. It will also be 0 everywhere. And in all other faces of the graph, anyway, I only see 0 edges along the face. So this is an example of a one form on a torus, which has 0 value along this discrete derivative. But this one does not arise as the gradient of a 0 form. Why? Because if you want to produce this gradient, maybe you want to put a 0 value here, and then you will jump to a 1 value, but that doesn't work. So Poincaré lemma is not always as simply stated as this one. Maybe you need to add some harmonic forms into the business, but we don't need.
This is also not a planar graph, right, for torus?
Right. It's not, yes. But I was not super careful in my setup. But if you take a planar graph, then Poincaré is robust, no problem. So I don't know if I want to give an example, but if df is 0, it means the sum of those is equal to 0, and you can hope to find a 0 form which is consistent with this locally, propagate this, and there are no issues like that will arise by the planarity. So the proof of Poincaré lemma is very easy, but I will not do it.
Christophe, I'm sorry, I'm just a little bit confused with the scalar product, because there you need some scalar product on each one of the omega I.
Yeah, it's not the same scalar product.
It's not, but what is the one on the right, for instance?
So the one on the left is a sum over all directed edges of the value carried by one times the value carried by the other one. Or it's the same, you fix an arbitrary orientation and you sum on those. Maybe you have to be careful with the factor 1/2. And this is the sum over the faces of the value of these two forms on the faces times these two forms on the same faces. Yes, L2 scalar product on each omega 0, omega 1, omega 2.
But for the generality of the theory, you need a sort of compatibility between the scalar products or something like this.
Yes, and you have to be a bit careful with boundary conditions. Yeah. But
I'm good.
Good, so I'm almost to have Poincaré, and I only need to do two other things and then we can start the proof. I need to tell you very shortly about what the Laplacian is. And I need to tell you about Hodge decomposition, which sounds fancy, but it will not be fancy. But it will be useful though. So, definition of Laplacian. And it's a very nice definition. So geometers, they use this all the time, but I must say I didn't know about it 6 years ago, I think. And since I know it, it clarifies many, many talks. So I'm super happy with this definition because it gives a Laplacian on the 0 form, the 1 form, the 2 forms, the k forms at once, and it's very compact. And it's just this. So this gives an operator, this defines negative semi-definite, I don't know how to say that, but negative semi-definite operator on omega 0, omega 1, omega 2 at once. And if you play with this operator, say on the 0 forms, on the 1 forms, I think this is, at least for me, this was not something standard at all before. But if you play with this operator on the 0 forms, you will exactly recognize a second discrete derivative. And as Yilin pointed out, if you play with this exact operator on the 2 forms, you will exactly recognize a discrete second derivative on the faces, which is exactly like, you will see the duality there. On the 1 forms, you will see something a bit more rich, because on the 0 forms, only this one is important. On the 2 forms, only this one is important. But on the 1 forms, both are non-trivial. And so the Laplacian on the 0 forms is quite interesting. If you want to read more about this, I'm sure there are zillions of places. But with Avelio Sepulveda, we really need to understand this. And we have a section on the Laplacian on the 1 forms, and on the Laplacian on the 1 forms, and the GFF on the 1 forms decouples nicely into several scalar GFF. So I think this would be one among zillions possible places where to understand this operator well. So maybe the work I did with Avelio, maybe around 21. It has a very long title that I forgot. Cool. You can ask me if you wish. So that's the Laplacian, and it's nearly negative definite on those, except here and there one has to be a little bit careful with the boundary condition of the Laplacian. Is it Neumann? Is it Dirichlet? Is it? But here we don't even have to be so careful. It will be invertible. And the last thing I want to tell you about is the Hodge decomposition. So proposition, Hodge decomposition. And here, just for the fun, I will give you 4 exercises to appreciate the concept. So for each one form, f, I claim that there is a unique decomposition of f into f is equal to d of a 0 form G plus d star of a 2 form. So there exists a unique pair of 0 and 2 forms such that f is equal to this. So the uniqueness, maybe you will suddenly don't fully agree here. I need to prescribe boundary condition. For example, if I had a 0 form G and I shift it by a constant value, it will produce exactly the same gradient field. So it's a unique modulo some routing procedure. Maybe so that you don't trick me with questions, I will say modulo additive constant or modulo boundary condition. So Hodge decomposition, especially for those one forms, is very useful. And the exercises that I prepared, there are more things to visualize what is going on. So the first one, I have my finite piece of Z2. And now it's no longer the torus. Imagine that my one form is this field of edges which are equal to 2, for example. And this is a piece of Z2 lattice. What is the Hodge decomposition of this? The exercise is made to be easily solvable here. So here you can put, for example, 0 values everywhere here and 2 values everywhere here. And when you will take the gradient, the d, only those edges will carry 2 minus 0. So if I put 0 everywhere here and 2 here, I solve this exercise 1. Exercise 2. If I have my piece of Z2 lattice, all the edges are 0 except maybe those 4 edges that have value 3. So if I see this one form, in fact, we can recognize that this one form is just arises out of the 0 form with 0 everywhere and 3 at this vertex here. And then the gradient field will catch 3 for all the coming edges here. A third example. So of course at some point I have to slowly go to the 2 forms, otherwise my exercises are not well prepared. So my third example is a one form which is 0 everywhere, but then it has a, okay, let me make it a little bit nicer. Okay, so imagine that I have 2 here, 2 here, 2, 2, 2, 2, 2, 2, and 1, 1, 1, 1. How do you do the Hodge decomposition of this? So I will put values 2 here, 2 here, 2 here, 2 here, and 1 here. So this is the two forms on the plaquettes, and I claim that the D star of these two forms will produce those cycles here. So this one is also simple to design because I just took a two form and I take the D star. The fourth example is a bit nicer. I will solve it in 10 minutes because I will need it. Imagine that my one form is even simpler. It's 0 everywhere. But in this edge, this unique edge, I put 1. This, I claim, is a bit less, is a bit more nasty as an exercise. I mean, it's not horrible, but the Hodge decomposition of this one will need both a contribution of 0 forms and also of 2 forms. And I don't yet tell you how. So now, in my timing, I'm 40 minutes late, which is great. But now I'm done with my crash course, and we want to start to prove, unless there are questions that I'm still happy to take, despite my timing. Don't hesitate. But then, otherwise, I will start the proof of the decoupling of the partition function.
There's actually something that I don't understand in the corollary of the decoupling of the partition function. The fact that
sorry, no, it's the corollary I stated is a corollary of the fluctuation field. It doesn't readily follow from the factorization of the partition function themselves.
But the fact that the coupling, the fact that the Villa model, the D form of the one form of the Villa model splits as
okay, it's a corollary of this. Yes.
The GFF plus the Coulomb, well, the D star of the Coulomb gas. Mm-hmm. Well, the D of the Villa model is supposedly a closed one form, and D of the GFF model is as well a closed one form. So it seems that on the Hodge decomposition, it should have only.
It's a very good question. It's a very good question. The detail is in the modulo 2 pi. So the d theta is not equal without the modulo 2 pi to the d phi. I see it only half answers your question. Okay, so I will prove the decoupling of partition function, and I claim that the proposition I stated is doesn't use important order tools, and then I will collect some fruits. So the proof will rely on most of those properties. So proof of Z villain equals Z GFF times Z Coulomb. And here I state it without 2 pi and anything, just to make it clear what we're doing. So let me start the proof with recalling what is the partition function of the villain model, and I will do free boundary condition here. So this, by definition, is so this is the constant, so that the models I defined earlier are indeed proper probability distributions. So this is the normalization constant to make sure we are working with probability. So this will be the integral over 0 to pi to the power lambda. I have product of d theta I, and now I have the interaction term, which is product I to j exponential minus b. No, I forget the main part, which is sum over the integers m in z exponential minus beta over 2 d theta ij plus 2 pi m squared. Okay, so here I will be a little bit fuzzy on this, so I warn now. This could be either a product over a chosen direction for each edge, or I would take a product over all directed edges, and then I need to divide by 4, because each edge would come with half of the interaction. And both of these cases are good. Both of these cases induce brain turbulences, but they're never really important. So the message is we'll not be too picky with those. They may be important for beta or beta over 2. This may be important, but for the phenomenology, they are not important. And I will do a first step in the proof, which is very classical in statistical physics, which is inverting product and sums. So this is often very useful. We also do this for the certain expansions of the Ising model. And when we do this, we are no longer summing over just one integer, but we're summing over a field of integers which are indexed by the edges of my graph. So now I'm summing over basically one forms, or z to the power directed edges of my graph, and maybe I only keep track of one directed edge per non-directed edge. And I still have the integral over all the d theta I, but now each edge has one integer to work with, exponential minus beta over 2, theta I minus theta j plus 2 pi mij squared. So here I am playing with a one form along ij of my angles, and also a one form which is z-valued along my edge. The very main idea of the proof, and I really like it, I really like this idea, is to reorganize, and this goes back to this paper in '77, is to reorganize this sum here. And the way they reorganize it is to say that the sum over integers, in some sense, this is describing how the Brownian bridges are behaving along each of the edges. This sum will be reorganized according to how far this one form is from an exact one form. And that's one way to picture the topological defect. We will reorganize this sum depending on how complicated this one form is. And that's where the vortices will pop out. So let me just rewrite this as sum over what they call topological defects, but here it will be a simple object. It will be a two form. It will be q in z to the power of the faces of the graph. So we start having an indication of the Coulomb gas which comes up. And I want the same sum on the left and here. So I will sum over all the one forms. I will do one running mistake in my whole computation, but I will tell you where eventually. But it's not quite yet here, so don't panic. So I will sum over q, sum over m, but those have to be very particular one forms that are encoded by this q. And what is the encoding? I only want to sum over the one forms m, which are such that dm is equal to q. So q is telling me what are the defects on each plaquette for this one form m. So this is the sum on the left is the same as the sum on the right. So and now I have the same thing in the middle. So integral over d theta exponential minus beta over 2, and maybe now I can write it. No, I will write it the same. So d theta ij plus m ij squared. So now, for each q, so claim for each q, I claim that there exists one nq. It is not unique, but I will choose one which is such that the differential of nq is equal to q. So there exists a one form NQ, which is such that I have D of NQ is equal to Q. In this line, I am using one of the properties. I am using this property here, that if I have any two form, there exists a one form, I forgot this, a one form F, such that D of F is equal to W. So I'm using this property here. And for each Q, here there is some, I could do many choices, but I need to pick one. There will be some change of variable later, and we will see that it doesn't depend on this choice I am making here. Why do I do this? This choice allows me to be a bit more explicit on the sum that I have here. So I'm claiming that the field of one form M such that dm is equal to Q is in bijection with the field of a zero form in Z to the power the vertices of the graph in such a way that each M which satisfies dm is equal to Q can be written as so the bijection reads as follows: M will be equal to D of psi plus N of Q. Okay, so proof of this, do I need to prove this? Maybe if M and M prime are such that dm equals dm prime equals Q, then D of M minus M prime is equals to 0. And so M minus M prime is equal to D of some psi, some function psi. This is Poincaré lemma. And so M is equal to M prime plus D psi. Okay, it's a terrible proof. It's not exactly what I want to do.
Just take M prime to be MQ.
Yes, yeah, I think that's what I want to do. Thank you. So any M is this, satisfies dm equals dnq equals q. And so dm minus this arbitrary choice that I made is equal to 0. And indeed, I apply Poincaré's lemma to this M minus nq. And so M is equal to nq plus D of psi. So we are almost there. I use this bijection here to say that my partition function is now equal to sum over Q in Z to the faces of lambda. And the bijection is nicer because instead of summing over one forms which have this topological constraint that D of M is equal to Q, I am summing just about 0 forms, which is much nicer. And now that I have this, the integral look as follows. And there will be the second nice idea of the proof. I will have product over edges, exponential minus beta over 2. And now I will write a bit more carefully what is the M. So I have d theta ij plus M is now d psi. So I have d psi along ij. And I have this nq1 form that I don't really know what. This one is a little bit arbitrary. It would be nice that we remove arbitrariness at this stage. I have something like that. So maybe I should do one example of NQ. I wanted to do it before. Example of NQ. let's imagine that in my graph, my field of integer maybe I have a 3 here, maybe I have -2 here, and maybe I have -1 over here. How do I find a one-form NQ which is such that D of NQ is equal to this? So I'm basically doing Poincaré's lemma on one-forms. But we will see something which starts looking like an interaction of Coulomb gas, even though there is no statistical physics at this stage. I can put a path which goes from 3 to -2 like that, with just one forms yellow that have values 2 here. So if I do this, I will produce almost 3 by doing the rotational of this one form here. But not quite, I still have this one to do. So this one, I will do one pass like that of things that have value 1 this time. And this one indeed carries -1, the rotational goes the other way, carries -1. This one indeed carries -2, and this one does carry 2. So if you see a field of integers, you just need to find suitable paths to go from one positive charge to a negative one. And one see here that the NQ is far from being unique. I could take any other path from 3 to 2 and it works equally well. You may argue that maybe I was not careful with the conditions, and maybe if I have just 3 here, and therefore a non-neutral plaquette with 3 in the middle and nothing else, maybe I am in trouble, because I could see Franco a bit with the neutrality. I am not in trouble, but I did not define things properly enough, but I am not in trouble because I do this one form all the way to here. And here I did not specify, but there is an outer face. And I put 3 everywhere. And the non-neutrality is absorbed by the outer face. And it's not an arnaque, I don't know the word. In some sense, the villain model, if it's free boundary condition, it's very well allowed to do a 3 pi monodromy at the outer boundary of its free boundary condition. So there is no, it's perfectly legitimate to do something like that. So that's why I've chosen free boundary condition, because I didn't want to constrain my Q to be neutral. Okay, and now I can go back to the exercise that I left over here. Why? Because it would be very nice to use Hodge decomposition on this one. If I could write this as D over 0 form plus D star over 2 form, then I will have D over 0 form plus D star over 2 form, and they are orthogonal to each other. So this L2, I forgot a very important square. This is the L2 norm square of one form. By orthogonality, if I could split this into the 2 contributions of the Hodge decomposition, I will put those 2 L2 squared contributions aside, and this will be the source of the decoupling. So the first big step is to think of rewriting the sum depending on the topological constraint. The second big step is to think of Hodge decomposition here to split the energy into 2 parts. So how do we solve this exercise? This could be an NQ. This would be the NQ, for example, of 1 here minus 1 here. That would be the NQ of this field of charges. How do I write any such one form, for example this one, as the sum of 2? I will solve the exercise in the general case. How to write NQ as D over 0 form plus D star of a 2 form, namely how do I do Hodge on this one? the trick is to use the fact that which I didn't prove, but the fact that the Laplacian is invertible on the one forms. So let me just write it like that. It's Laplacian inverse of NQ. And let's remember what the Laplacian is. The Laplacian is d star plus d star d Laplacian inverse NQ. And there is another property which is very convenient. Since the Laplacian is made of this d star, it turns out that Laplacian and Laplacian inverse, they do commute with d and d star, which is very convenient. So let me use this. So this will be d of d star Laplacian inverse NQ plus the other one is d star Laplacian inverse, and I did it the other way around, sorry. D star plus d star, this is better like that. No, this is worse. Sorry. So that was good actually, d star, and this I can commute it with Laplacian inverse, and that's nice because d of NQ by definition is Q, and I remove the arbitrariness just on the side of the two forms. So here I have Q. So let me inject what Hodge decomposition tells me into this computation of the partition function, and we will be basically done. So now I will go fast because the main two ideas are behind us. The rest is just calculations. So Z is equal to sum over Q. This one is important. Sum over psi. Integral over d theta of exponential minus beta over 2. And I will write it like that. Scalar product of d theta ij plus d psi ij plus d Laplacian, there are some 2 pi that I forgot. They are not very important, but there are 2 pi's everywhere here. I think I forgot those here. There is a 2 pi here. So there is 2 pi d psi ij plus 2 pi d d star Laplacian inverse NQ. This one is nasty but will not play any role. Plus d star Laplacian inverse Q. All those are one forms, they're around ij. And I have this norm squared. So now I can use another property that I listed before, which is that the d of the zero form are orthogonal with respect to the d star of the two forms. So this I can rewrite it, sum over Q, sum over psi, integral d theta, and I will do it better, I will do 2 steps at once. By orthogonality, this L2 norm squared is the sum of this L2 norm squared plus this L2 norm squared. But this one, thankfully, only depends on Q. And since it only depends on Q, when I sum over Q, I can keep track of this estimate here, which has, there is a 2 pi. And now we see the 2 pi squared coming out, and we see L2 norm squared of d star Laplacian inverse Q against d star Laplacian inverse Q. So maybe my crash course would have been a little bit better with specifying those scalar products, I am sorry. This was Lucas' question. And I'm now left with sum over psi of integral over d theta exponential minus beta over 2 d of many things squared. So I will rewrite this a little bit in a nicer way. I have sum over q exponential minus beta over 2, 2 pi squared. And what can I do here? I can use the fact that d star is minus adjoint. So this is minus Laplacian inverse q against d star Laplacian inverse q. I just did put this on the other side and use the fact that d star is minus adjoint. But now, in fact, this is just identity. This is because the Laplacian on the two forms only fills half of the definition of the Laplacian. So this is, and I forgot a very important minus. So there's a minus here because it's minus the adjoint. So all this is, I can rewrite it like as q minus Laplacian inverse against q. And this is positive semi-definite on the two forms and not negative. So the signs are correct.
So on the second line, perhaps it's d star times d, then minus the inverse of Laplacian, because q is one form. If we write like this will be zero. A zero form, sorry. Q is zero.
Q is a two form.
Oh, it's a two form.
Yeah.
Oh, in that case, okay.
Yes. Otherwise, yes, I mean, yes.
Yeah.
But thank you. So we are done with the Coulomb term. The only thing we need to prove, and I want to say other things. So maybe I can draw one picture why this is just GFF. I will write one formula because the cheat is there. So maybe I still need to say it. So. We could be worried about one thing, which is that we do have our Coulomb term, but if I write down this sum over psi, there is still a bit of Q dependency in this integral, and we don't want any Q dependency if we want a pure decoupling. So maybe because we're a little bit worried, let me still write this down, but not spending too much time. So let's show that the GFF, is it indeed, do we have good reasons to believe that this is equal to this sum, which seems to be Q dependent? Sum over psi, integral d theta, exponential minus beta over 2. And I have d theta plus psi plus whatever came out of Hodge decomposition, which was, I think, d star. I have 2 pi's everywhere, 2 pi psi plus 2 pi d star Laplacian inverse of q. Yes. This norm squared. Why is this a GFF? So maybe let me imagine. Let me draw the two-dimensional box. Lambda. And let me just draw the contribution of the partition function on the vertices at the bottom. This integral is integrating from 0 to 2 pi on all the vertices of my graph lambda. So what I claim is that along each point in my graph, for a GFF partition function I want to integrate over R, what do I see? I see a very nasty term, which is this oh, I want NQ. I want NQ, otherwise I think I'm not happy. Yes, yes. Yes, I want NQ because this is a 1 form, this is a 0 form, so this is well defined on the vertices. So maybe here I have something which does see Q, maybe this is 2 pi d star Laplacian inverse of this very artificial NQ. Maybe here I have another d star Laplacian inverse NQ, maybe here I have this. I have some values which do fill the Q configuration that I have chosen. On top of these fixed values, I'm integrating over the angle 2 pi. So on top of it, I'm adding an integral over 2 pi, which is a uniform integral here over 2 pi. This is still not very good, but I'm also summing over z-valued integers. In fact, 2 pi z-values integers. And this is now very nice, because when I sum over those, the measure that I see everywhere is a compilation of all these uniform measures. And this is restoring the Lebesgue measure on top of each point of my graph. And that's why I don't do the details, but it's really the picture to me which closes everything. This is why we get GFF. Where did I cheat before I moved to something else? I did cheat because if we have that, we have an integral over a non-rooted GFF measure, which is infinite. So in fact, since the very beginning, I had to root my system at some vertex somewhere. If for the free boundary condition villain, I can always decide that the x0 point anywhere in my graph is set to 0 and say that my partition function is 2 pi times this. And once I set x0 to be 0, maybe this is this point here, this point is just 0, we don't integrate on anything, and this is rooting the GFF, which will be the free GFF. Okay, so the only cheat is that I didn't root anything. So in fact, at some point when I told you there is a bijection, this was not quite correct, because I could also add psi plus c, and this would also be correct. So I needed to root at some point. And I made the mistake on my notebook, and then I was, what's going on? And then I remembered the routing, so I thought the routing only comes a posteriori. Okay, so in the 15 minutes that remain, I hope to do two things. Yes.
So, for instance, your proof is quite geometric, so it is done in the discrete case. Would the adaptive be continuous, although there was a problem there?
So this would be a bit related to Yilin's question that all those Hodge decomposition and this structure, you can still do it in the continuum. What's less clear is what would be a nice enough proistic model which would not be too fluctuating, so that you would still see pointwise vortices and for which you could do all this. And it's not impossible, it exists and it's nice, but you would need to have a gas of vortices in R2, and then maybe you get closer to what Sylvia Sarfati, Jeanne Boursier are doing lately with Coulomb gas in R2 that are attracting, repelling each other. And it would be very nice if it would be very related, but it seems if you do things naively, they will cluster together too quickly and you will not see anything in the... So you need to also counter-effect this attraction mechanism, which is a bit related to BKT, so it's not clear. But it's a good question.
Is it possible to adapt this approach to, let's say, model on a torus?
Yes, it's also a good question. So yes, it works pretty well. And in fact, I was doing this with a PhD student a while ago. And what pops out very, very naturally is that you get the compactified GFF, which pops out very nicely. But yeah, so you get a decoupling of a compactified GFF, and I don't know if it's not very hard, and this is something important in with dimers, for example. So here it's simpler in some sense. The decoupling is, and there you need to say that the Hodge you need to be a bit more careful with the harmonic forms. Okay, so okay, so I have two options, but I have already decided. So, but it's advertisement for tomorrow. So tomorrow, so that was my first option. Tomorrow, when we'll go into the proof of BKT, when we will have a piece of a Z2 lattice, we will use the fact that along each edge, we will Fourier transform the interaction to have a Z-valued interaction along each edge. And in some sense, we will repeat some of the things we have done today, namely, we will have a statistical physics model on Z-valued one forms, and it will be good to play with those, not quite Hodge decomposition, but we'll not play with Coulomb, but we'll play with the dual of Coulomb, which is a Gaussian free field, very nice, quadratic interaction, but conditioned to be Z-valued. And for this, I will have to rewrite the partition function of the villain model using the Fourier transform of S1 along all the edges, and we will see that Z of villain, instead of being equal to Z of GFF times Z of Coulomb, will be exactly Z of integer value GFF. And here there will be one consequence of the usual thing of Fourier analysis with I forgot this term of quantum mechanics, uncertainty principle. The temperature will be inversed. And so all the analyses will focus, if we're interested in low temperature villain, will be forced to understand high temperature Z-valued interfaces. So tomorrow, I will again do an expansion of a partition function. I will go slowly into a Z-valued partition function. And we will see now, I mean, to prove BKT, I will not be able to stay at the level of partition function. Otherwise, we'll not have polynomial decay of correlation. So what I will need to do, which is a very standard step in statistical physics, I will need to do the same procedure when I also want to remember the information at the angle at x and the angle at y. And this will be the same type of partition function, but it will be modified because of the presence of x and y. But since we've done many computations today, and I will go through it, this will be natural tomorrow, but today I think we're a bit too tired for that. So my second option, which is my choice, in the last 10 minutes, now I have two choices actually. Either I give you a list of BKT models that I wanted to do in lecture 1. Maybe I'll do in lecture 4, that's okay. Or I tell you what can we extract out of the decoupling of Coulomb. And I think I will also make a choice here, because otherwise why do we do this whole decoupling? So I will give you a few applications of this decoupling I just stated. And I mean, I will not do all because I have 10 minutes, but there are a few nice ones. Okay, so application 1, we've already seen that it gives a very soft proof of upper bound of polynomial decay, which is much better than the proof I gave in lecture 1, which gave logarithmic, though it does not give power law decay of correlation of the total variation distance. So the lecture 1 still had some interest in this regard. So application 1 is an easy proof of McBrien Spencer for villain. Application 1 bis is that in the computation I showed to you here, I just said the two-point function of villain decouples into the two-point function of a GFF times a nasty type of two-point function on the Coulomb side. If you also want to use the strengths of this Coulomb Coulomb participation to the fluctuation, with Avelio Sepulveda, we could prove that sigma x scalar product with sigma y in the villain model in Z2 at inverse temperature beta is less than 1 over 2 pi, no, 1 over Euclidean distance between x and y at large distances. So this is the spin wave upper bound of a Mac-Bryan-Spencer type that we reproved. And we could add a little bit more to the story, which is the vortex contribution. And this C, to some extent, we got the optimal C. So we got the optimal C in the large beta regime on the size of the free energy. For the 2-point function, we miss the optimal one by a factor of 2. So that's application 1 bis. So application 2, it implies a local algorithm to sample a Coulomb gas, to sample Q weighted according to exponential minus beta 2 pi squared over 2 Q against minus Laplacian inverse of Q. And if you look at this statistical physics model in the way that it's written as Qi, Qj, green function between I and j, this is severely non-local. So if you were to do a Glauber type of dynamics to sample those, at each step you would need to look at the sea of charges in your old Z2 lattice before you replace with a new charge. This viewpoint allows you to have, I think, a much faster algorithm, though we never did it on a... Maybe Avelio actually did something nice. But I was thinking of asking Werner Krauss, or because they did simulations of S1 valued spins, to first do the villain until equilibrium, and then in a local way output the Coulomb gas. So that's application 2. Application 3, which is very related, and this one I am very happy about it, so we didn't write it down yet, and it's my fault, it's not Avelio. Application 3, we get a very short proof at high temperature of the bi-screening of Coulomb gases on ZD. The bi-screening of Coulomb gas on ZD. So I will just do Z2 here, and Z2, the fact it's only at high temperature is good because it's known to be wrong at low temperature. In Z3, it's proved to be the case at whole temperatures, but it's a very difficult theorem. So our proof only works at high temperature. So what does it mean, the bi-screening? If you do maybe it's not chemistry, but plasma physics, so which I don't do, but I think this is a concept quite important there. If you have ion, I don't know how we say ion, but okay, let's say ions maybe. So if you have ions, and it's very high temperature, so the electrons, they went away from those ions, and the plasma is meant to say that it's so hot that the electrons are not associated to the ions. In plasma physics, they say that if you put a big charge over here, the electrons will organize themselves quickly around this to screen the charge and make it invisible seen from far away. And it's a very important concept in plasma physics, and with Avelio, in this thing we didn't yet write down because of me. We made 3 definitions of Debye screening. One is a bit like that. One is in terms of decay of correlation of the Coulomb particles. Another one is in terms of partition functions. And for all of those, we can say that there is a Debye screening. So let me make a proof of this, a 1-minute proof. I will just do expectation Qx, Qy. So let me multiply the charge at x times the charge at y. And I want to tell you that this is less than exponential minus a constant times the distance. So this is exponential decay of correlation of the z integer charges. And to me, this definition of Debye screening was always mysterious. How come this system, which has very long range interaction, logarithmic interaction, organizes itself in such a way that when you look at the charges here, it says nothing on what the charges are doing far from where you are. So the proof is like that. Let me take this little face in Z2 and let's visualize the charge which is here. The danger is that this is non-compact. It could be that the charge is enormous there. Let's say that the charge is 10 to the 6 plus 4. Just to be... maybe I'll take the questions at the end if you don't mind. So let's say you have a huge number. So this is very non-compact, but in our proof, which is just a few lines, we say the following. Let's compute the law of the Villain model in the whole Z2, which is conditioned to produce 10 to the 6 plus 4 in this placket. This is a very complicated law. We have no idea what this is, but whatever this is, S1 is compact, so it will output 4 angles at the 4 vertices here, which are conditioned in such a way that the concatenation of 4 Brownian bridges will produce 10 to the 6 plus 4. So in fact, they better be very equally placed, but we don't care. Very complicated conditioning, and it's also a conditioning which is the whole Z2. Whatever we see here, it's compact. So if I want to go to the placket Y, which is very far away, now I can go to the Villain model. And the Villain model is at high temperature, so by the time I will travel to the placket Y, I know by standard Markov chain techniques that I completely forgot what happened over there, despite the 10 to the 6 plus 4. So what I see here is an exponentially uncorrelated field of angles given what I had here. And now that I have here, I produce the Brownian bridges and I produce the Q of Y, which basically doesn't care what it sees there. And it proves the Debye screening. So that's application 3. It's 4 p.m., so I will give 2 more without proving or saying anything. And then we have tea down here for those who were not here last week. So application 3, not 4, I don't know. Application n plus 1. Application 4. Coulomb gas is rigid. So this is something that I'm doing with David de Reudre in Lille. And we're late also because of me. And in Z3, the story is more interesting, but let me just say in Z2, if you sample a Coulomb gas in Z2, on the whole Z2, so maybe application 5, I have the wrong order. The probability measure on lambda n Coulomb beta, it converges when n goes to infinity to a Coulomb gas on the whole Z2. And this one doesn't see free versus Dirichlet boundary condition, which is maybe not completely clear to start with. And now that we have this, we have a very intrinsic Coulomb gas in the whole grid. And it's rigid in the sense that if I look at the field of integers on my placket, on the whole plane, and if I remove the charges that I have in this box, if I give you this sigma field, if I give you all those integers to you, it's rigid in the sense that you can recover exactly the arithmetic sum of integers which is hidden here. So not at all like if you had a Poisson point process, for example. So it's a nice example, I think, of a rigid system. And there is another, and the last one I just make a drawing. Because the last one, we have a very short proof of this, and a proof of this for the analogous two-component model in R2 is a very deep theorem of Thomas-Leblay, and on other settings is very difficult. If I take any shape in ZD, so it works on Z3, and I ask myself, what is the variance of the total charge inside this box? We have a very short proof that the variance is less than the size of the boundary, and this is called area law. And for those two-component Coulomb gas in R2 or RD, this is extremely hard, I believe, to prove even hyperuniformity, which is little o of volume. Here we just get area law out of all this going back and forth between Villain and Coulomb gas. So I think 3 minutes off. I will be very happy to answer questions after, but I will stop here.
This one, perhaps stupid question. In your definition of the bias screening, perhaps it's better to put an absolute value in the expectation, right?
If I put absolute value here, then it will not be exponentially small. It would be only the truncated one, which would be, and the proof also gives the truncated one here. But if I only put absolute values, there is positive probability that this is 2 and this is 2, so it cannot go to 0.
And this is perhaps, if you write in terms of x, y, Villain, this will be like an 8-point function. And normally what you have is exponential decay for a 2-point function, but for the 8-point function, can it be derived from the 2-point?
Okay, so yes, so I think that's an excellent question. So at least for those type of questions, to know if the variance is very small compared to volume, there is a long series of work by Leibovitz in the 80s, which say that if you have a good control on the 2-point function, then you know that your system needs to be hyper-uniform. And the difficulty often is that the 2-point function is hard to have access to this. And the relation with the Villain is that at low temperature, this is going to be polynomially decaying, but the power is important to go into Leibovitz or not. I don't know if it's exactly the question, but it looked a bit like it.
So I have a question about this rigidity. So suppose you sort of sample everything, but you don't sample what happens in one square.
Yes.
But then you don't force it to be an integer, but you allow it to be like just a real number.
Okay.
What would the distribution look like? Would it be like concentrated as an integer, or would it be sort of randomly distributed in the interval, but then it's not exactly at 1/2, and therefore you're forced to be an integer? Or
so you mean you relax the Coulomb gas by relaxing just at this point, and you ask whether you are still rigid or not?
Yes, and if you could also be rigid, but that it doesn't become an integer.
Yeah, I see. That's a good. I don't know. I would think that it would not be rigid, but as you said, this would be more and more Dirac depending on the beta.
Okay.
Something like that.
Thank you.
It's a good question.
So, is it possible that in the partition function of the Villain model, we use that ±1 trick to do cluster expansion so as to calculate the free energy? I mean, in series expansion.
Which plus-minus trick?
There we had exponential of.
You mean the splitting in Q and M separately, this one, or? We can also discuss if you. Nathan, you had a question just.
No, but it was the same question with the absolute value.
Oh.
Maybe a more naive question about what would you expect to happen if you go into a non-Abelian case. Say you replace U1, the unit circle, by a non-Abelian like SU2 or CO3 or anything else. Would you expect to have such decoupling?
Yeah, so it's a very good question. So maybe in the last lecture, at least I wanted to do it initially, with a Ioannaru and Avelio Sepulveda. So certainly we didn't do the harmonic analysis of the non-Abelian groups. This would be maybe a potential path towards Polyakov, but there are many issues along the road. But what we did, we imagine what would be the projection of those systems down to an abelian. So the S2 sphere, you can project it to the S1. And we analyzed what kind of random disorder could be compatible with Polyakov. And in this setting, we would keep this structure, but now the coupling constant would be random. And the question would be to which extent the non-Debye screening is robust to the presence of disorder. And we have results in this direction that are compatible with Polyakov, but they don't prove. They're just... But otherwise, if it's non-Abelian, decoupling... let me just say, if you have S2, maybe you want to say that there is a GFF in the tangent space, a two-component GFF. But then this two-component GFF will not... it's not like on the circle where there is a very nice folding, I don't know the word, but lifting, yes, thank you. On S2, locally it's great, but eventually it's bad, and probably the creation of the mass is exactly because of this. So I don't expect a nice, beautiful decoupling, because there is something much nicer, much more difficult to... The lack of BKT there is considered much more nice.
Any other questions?
So there, if we introduce -1 + 1, so as when we do the, in the summation integral d theta, that expression.
This blackboard?
Yes, sir, at the top.
This.
No, sir. The exponential expression, exponential minus beta by 2.
Yes.
So I was saying, if we do exponential of this thing, entire thing, -1 + 1, and when we are doing product over all the edges, then we can get the over
I see what you mean. Yes, there are notions of cluster expansion in this setting, but they wouldn't do this -1 + 1 trick. The issue is that maybe your theta is going to be small, but the psi you're currently working with is not really small here, and the -1 + 1 is not going to capture what you would want in a cluster expansion. So yes, there are some type of cluster expansion, but not like you would do in Ising with a +1 - 1 to then distribute. But yes, it's a good question.
If there are no more questions?